Welcome to Linear Optimization, and today we're going to go over some setup and notation. The standard form of a linear program is given as a minimization of a cost function, where I take a vector and I dot product with another vector, and I say that the x's are my variables, but I want to restrict those variables such that they are a solution to the linear equation ax equals b, and also all of the variables are non-negative. It's important that when we think about x as a sequence of n variables put together into a column vector. The cost vector, c, is also a sequence of n real numbers assigning to the cost of having that much value of xi. However, the vector b is a column vector of m entries, because in order for this linear system to hold, the important part is that A is an m by n matrix. Take my m by n matrix, multiply it by my n length vector, and I get a vector of length m. We will typically think of m, because we have a sequence of equalities, m must be at most n. We will make a few assumptions about our system for now, and we will deal with that issue later. Our first assumption is that the rank of our matrix A is m, which means that full rank, and we have m linearly independent columns within A. Our second assumption is that the set of feasible points is non-empty. There's at least one point which satisfies this equation and all the variables are non-negative. We will also assume that if I consider my cost function, c dot x, for all feasible points, that set is bounded from below. This allows us to actually say that a minimum does exist, because we don't have an infinite sequence going off towards negative infinity. We will consider these assumptions and we will remove them one by one as we get more detail into our algorithms. But it is most important that we are always considering about these constraints. Our next step is given our linear system just these constraints, being able to find solutions that make sense for us. What we will do is we'll restrict to a certain set of the variables by looking at a certain set of the columns. Throughout, we will always fix some basis script db of m columns of A. So I say A sub j1 is the j1th column of A, and so on and so forth for m of them. And the order of these columns that I select in the basis is important. So this is a set of m linearly independent columns of A. When I have such a sequence, when we have such a linear independent set, because all of these columns are living within Rm, this must be a basis for that full space, which means that all other columns of A are linear combinations of these columns. And also, we can solve this system very quickly in the following way. So, from these columns, we can build a matrix by putting those columns all in a row. And what we have is an m by m invertible matrix, because all of the columns are linearly independent. From that, we can see that the linear system of equations bx0 equals b actually has a unique solution. What is x0? What we will do is use x0 to denote the variables corresponding to the columns in our basis. So we have this smaller set of smaller vector x0, where we have x10, x20 all the way up to xm0. And this vector is corresponding to the ith coordinate of this vector is the variable xji, which is the variable corresponding to the column that we selected in our basis. What we are doing by solving this linear equation, we find this vector here, and then we take those values and place them in the variables here. And we want to retake that to build a solution up here. Well, what we can do is make the variables that are not in the basis be 0. So far, we have fixed a basis of columns within A, and we've solved this system of linear equations. So there's m equations for m variables. So we can take our set of n variables and we can define it in terms of, well, the jth variable is either equal to xi0 if the j is actually that column corresponding to the ith column of our basis, or we let it be 0 otherwise. And in this way, I have all of my variables that correspond to this. We call these basic variables. So our basic variables are the only ones allowed to have non-zero value. Everything that's not according to the basis is getting value 0. The question now is, this is now what's called a basic solution. So our vector x0 and our full vector x are both called basic solutions because they are solutions to this system with respect to this specific basis. The question that remains is, are these feasible solutions as well? Specifically, do they have non-negative value? So when I have my system, and we've fixed a basis and we've solved for x0, we then have a basic solution. If our basic solution also has non-negative value in every coordinate, then it is a basic feasible solution, or shortened BFS. We're going to use basic feasible solution so often that we're just going to shorten it as lowercase bfs. So when you see BFS, think basic feasible solution. We have a basis living somewhere, we have an x0 living somewhere, and we know how to translate from x0 into our full basic feasible solution, x. If we want, we can consider our basis and use a little bit of notation to help us know what the order of the basis is. So fixed a script B basis, and I have this matrix B. In addition, we have a function B, which takes a number from 1 to m, and it outputs another number. And that number is the column index in A of the ith basis element. This is important so we can maintain what order our basis is set in. The order is very, very important. Specifically, because we're going to express the other values of A, the other columns of A, in terms of our basis elements. If we restrict our cost vector to the columns of our basis in order, what this means is that I have my first basis element has a certain cost. My second basis element has another cost. And I now have a vector of m cost values from my original sequence of n cost values. We can compute this cost value of our basic feasible solution very quickly. So when I'm computing the dot product of the cost function restricted to our basis with x0, it's exactly the same as taking the cost function, the cost vector dot product with the full basic feasible solution. Because the things that are missing over here, that exist over here, these things are all 0. Because all the xi's that are not in x0 have value 0. But it's important that x0 and c sub b, the order of the variables matter, because it corresponds to the order of our basis. Finally, we want to keep track of representing the columns of A in terms of the columns in our basis B. We can define an m by n matrix X, capital X, with doubly indexed x values in the middle. Well, what I want to do with this is I want to look at an ith column of X. When I look at an ith column of X, I want that to be the representation of, when I look at the jth column of X, I want that to be the representation of the jth column of A with respect to the basis element. Specifically, I want xj to be the solution to this linear system of equations. If I take the columns of my basis and I multiply them by the elements of xj, I want to get the vector aj. Such an xj exists because B is invertible. So we have xj is the representation of aj in terms of the basis B. This actually can be written down in a more careful way using the formula by expanding this in terms of xj. So what this means is that if I look for I equal 1 to m, I look at the ith basis column, and I'm going to multiply that by xij. And that allows me to have a value of a sub j. Having this representation is going to be extremely useful, and that thinking about it as this big matrix allows us to store things and keep track of them in a very efficient way.